The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so last week we've learned how to do triple integrals in rectangular and cylindrical coordinates, and now we have to learn about spherical coordinates, which you will see are a lot of fun. So what's the idea of spherical coordinates? Well, you're going to represent a point in space using the distance to the origin and two angles. So in a way, you can think of these as a space analog of polar coordinates, because you just use distance to the origin, and then you have to use angles to determine in which direction you're going. So somehow they're more polar than cylindrical coordinates. So how do we do that? So let's say that you have a point in space at coordinates x, y, z. Then instead of using x, y, z, you will use, well, one thing you will use is the distance from the origin. And that is denoted by the Greek letter rho, which looks like a curly P, but actually it's the Greek R. So that's the distance from the origin. And so that can take values anywhere between 0 and infinity. Then we have to use two other angles. And so for that, let me actually draw the vertical half plane that contains our point, starting from the z-axis. Okay? So then we have two new angles. Well, one of them is not really new. One is new, that phi is the angle downward from the z-axis, and the other one, theta, is the angle counterclockwise from the x-axis. Okay, so phi let me do it better. So there's two ways to draw the letter phi, by the way. And I recommend this one because it doesn't look like a rho, so that's, easier. That's the angle that you have to go down from the positive z-axis. And so that angle varies from 0 when you're on the z-axis, increases to pi over 2 when you're in the xy plane, all the way to pi, or 180 degrees, when you're on the negative z-axis. It doesn't go beyond that. Okay. So phi is always between 0 and pi. And finally, the last one, theta, is just going to be the same as before. So it's the angle after you project to the xy plane, but the angle counterclockwise from the x-axis. Okay, so that's a little bit overwhelming, not just because of the new letters, but also because there's a lot of angles in there. So let me just try to, suggest two things that might help you a little bit. So one is, these are called spherical coordinates because if you fix the value of rho, then you're moving on a sphere centered at the origin. Okay, so let's look at what happens on a sphere centered at the origin. So with equation rho equals a, well, then phi measures how far south you're going. It measures the distance from the North Pole. So if you've learned about latitude and longitude in geography, well, phi and theta you can think of as latitude and longitude, except with slightly different conventions. Okay, so phi is more or less the same thing as latitude, in the sense that it measures how far north or south you are. The only difference is in geography, latitude is 0 on the equator and becomes, something north, something south, depending on how far you go from the equator. Here you measure latitude starting from the North Pole, which is at 0, increasing all the way to the South Pole, which is at pi. And theta you can think of as longitude, which measures how far you are east or west. So the Greenwich meridian would be here, now the one on the x-axis. That's the one you use as the origin for longitude. Okay. Now, if you don't like geography, here's another way to think about it. So let's start again from cylindrical coordinates, which hopefully you're kind of comfortable with now. Okay, so you know about cylindrical coordinates, where we have the z coordinate stays z, and in the xy plane we do r and theta, polar coordinates. And now let's think about what happens when you slice things, when you look just at one of these vertical planes containing the z-axis. So you have the z-axis, and then you have the direction away from the z-axis, which I will call r, just, because that's what r measures. Of course, r goes all around the z-axis, but I'm just doing a slice through one of these vertical half planes, fixing the value of theta. Then r, of course, is a polar coordinate seen from the point of view of the xy plane. But here it looks more like you have rectangular coordinates again. And so the idea of spherical coordinates is you're going to do polar coordinates again in the RZ plane. Okay, so if I have a point in here, then rho will be the distance from the origin, and phi will be the angle, except it's measured from the positive z-axis, not from the horizontal axis. But the idea in here, see, is, well, I'm going to put that between quotes because I'm not sure how correct that is, but in a way, you can think of this as polar coordinates in the RZ plane. So in particular, that's the key to understanding how to switch between spherical coordinates and cylindrical coordinates, and then all the way to x, y, z if you want, right? Because this picture here tells us how to express z and r in terms of rho and phi. So let's see how that works. If I project here or here, so this length is z, but it's also rho times cosine phi. Okay, so I get z equals rho cos phi. And if I look at r, it's the same thing, but on the other side. So r will be rho sine phi. Okay, so you can use this to switch back and forth between spherical and cylindrical. And of course, if you remember what x and y were in terms of r and theta, you can also keep doing this to figure out, oops. So x is r cos theta, that becomes rho sine phi cos theta. Y is r sine theta, so that becomes rho sine phi sine theta. And z is rho cos phi. But basically, you don't really need to remember these formulas as long as you remember, how to express r in terms of rho sine phi and x equals r cos theta. So now, of course, we're going to use spherical coordinates in situations where we have a lot of symmetry, and in particular where the z-axis plays a special role. Actually, that's the same with cylindrical coordinates. Cylindrical and spherical coordinates are set up so that the z-axis plays a special role. So that means whenever you have a geometric problem and you're not told how to choose your coordinates, it's probably wiser to try to center things on the z-axis. That's where these coordinates are the best adapted. Okay, and oh yeah, in case you ever need to switch backwards, I just want to point out, so rho is the square root of r squared plus z squared, which means it's the square root of x squared plus y squared plus z squared. Okay, so that's basically all the formulas about spherical coordinates. Okay, any questions about that? No? Okay, let's see. Who had seen spherical coordinates before? Just see. Okay, that's not very many. So I'm sure for one of you saw it twice. That's great. Okay. Sorry. Oops. Okay. So let's just look quickly at equations of certain things. So as I've said, if I set rho equals a, that will be just a sphere of radius a centered at the origin. More interesting things. Let's say I give you phi equals pi over 4. What do you think that looks like? Actually, let's take a quick poll on things. Okay, yeah, everyone seems to be saying it's a cone, and that's indeed the correct answer. So how do we see that? Well, phi, remember, phi is the angle downward from the z-axis. So let's say that I'm going to look first at what happens if I'm in the right half of the plane of the blackboard, so in the yz plane. Then phi is the angle downward from here, so if I want to get pi over 4, that's 45 degrees. That means I'm going to go diagonally like this. Of course, if I'm in the left half of the plane of the blackboard, it's going to be the same. I also take pi over 4, and I get the other half. And because the equation does not involve theta, it's all the same if I rotate my vertical plane around the z-axis. So I get the same picture in any of these vertical half planes, actually. Okay. Now, so this is phi equals pi over 4. And just in case, to point out to you what's going on, when phi equals pi over 4, cosine and sine are equal to each other. They're both 1 over root 2. So you can find, again, the equation of this thing in cylindrical coordinates, which I remind you was z equals r. Okay? In general, phi equals some given number, or z equals some number times r. That will be a cone centered on the z-axis. Okay, a special case. What if I say phi equals pi over 2? Yeah, it's just going to be the xy plane, okay? That's the flattest of all cones. Okay, so phi equals pi over 2 is going to be just the xy plane. And in general, if phi is less than pi over 2, then you're in the upper half space. If phi is more than pi over 2, you'll be in the lower half space. Okay. So that's pretty much all we need to know at this point. So what's next? Well, remember we were trying to do triple integrals. So now we're going to do triple integrals in spherical coordinates. And for that, we first need to understand what the volume element is. What will be dv? Okay, so dv will be something d rho, d phi, d theta. Or in any order that you want, but this one is usually the most convenient. So to find out what it is, well, we should look at how we're going to be slicing things now. Okay, so if you integrate d rho, d phi, d theta, it means that you're actually slicing your solid into little pieces that live somehow, if you set an interval of rows, okay, sorry, maybe I should. So if you first integrate over rho, it means that you will actually choose first a direction from the origin given by phi and theta. And in that direction, you will try to figure out how far does your region extend. And of course, how far that goes might depend on phi and theta. Then you will vary phi, so you have to know for a given value of theta, how far down does your solid extend. And finally, the value of theta will correspond to, in which directions around the z-axis do we go. So we're going to see that on examples. But before we can do that, we need to get the volume element. And so what I would like to suggest is that we need to figure out what is the volume of a small piece of solid which corresponds to a certain change, delta rho, delta phi, and delta theta. So delta rho means that you have two concentric spheres, and you're looking at a very thin shell in between them. And then you'll be looking at a piece of that spherical shell corresponding to small values of phi and theta. So because I'm stretching the limits of my ability to draw on the board, here's a picture. I'm going to try to reproduce that on the board. But so let's start by looking just at what happens on a sphere of radius a, and let's try to figure out the surface area element on the sphere in terms of phi and theta. And then we'll add the rho direction. Okay, so let me say, let's start by understanding surface area on a sphere of radius a. So that means we'll be looking at a little piece of the sphere corresponding to angles delta phi, and in that direction here, delta theta. Okay, so when you draw a map of the world on a globe, that's exactly what the grid lines form for you. So what's the area of this guy? Well, of course, all the sides are curvy. They're all on a sphere. None of them is straight. But still, if it's small enough, then it looks like a rectangle. So let's just try to figure out what are the sides of your rectangle. Okay, so let's see. Well, I think I need to draw a bigger picture of this guy. Okay, so this guy, so that's a piece of what's called a parallel in geography, okay? That's a circle that goes east-west. So now, this parallel is a circle of radius. Well, the radius is less than a because, if you're very close to the North Pole, it will be actually much smaller. So, that's why when you say that you're going around the world, it depends whether you do it at the equator or at the North Pole. It's much easier at the North Pole. So, anyway, okay, so, this is a piece of a circle of radius. Well, the radius is what I would call r, because that's the distance from the z-axis. Okay, that's actually pretty hard to see now. So if you can see it better on this one, then, so this guy here, this length is r. And r is just rho, well, rho is a times sine phi. Remember, we have this angle phi in here. I should use some color. Sorry, it's getting very cluttered. So we have this phi, and so r is going to be rho sine phi, but rho is a. So let me just put a sine phi. Okay, and the corresponding angle is going to be measured by theta. So the length of this is going to be a sine phi delta theta. That's for this side. Now, what about that side, the north-south side? Well, if you're moving north-south, it's not like east-west. you always have to go all the way from the North Pole to the South Pole. So that's actually a great circle, a meridian, of length, well, the radius is the radius of a sphere. Total length is 2 pi a. So this is a piece of a circle of radius a. And so now the length of this one is going to be a delta phi. Okay? So just to recap, this is a sine phi delta theta, and this guy here is a delta phi. So you can't read it because it's so that tells us that if I take a small piece of a sphere, then its surface area, delta S, is going to be approximately a sine phi delta theta times a delta phi, which I'm going to rewrite as a squared sine phi delta theta. So what that means is, say that I want to integrate something just on the surface of a sphere. Well, I would use phi and theta as my coordinates, and then to know how big a piece of a sphere is, I would just take a squared sine phi d theta. Okay, so that's the surface element on a sphere. Now what about going back into the third dimension, so adding some depth to these things? Well, I'm not going to try to draw a picture because you've seen that's slightly tricky. Well, let me try anyway. So just so you can have fun with my completely unreadable diagrams. So anyway, if you look at now, something that's a bit like that piece of sphere, but with some thickness to it. The thickness will be delta rho, and so the volume will be roughly the area of the thing on the sphere times the thickness. So I claim that we'll get basically the volume element just by multiplying things by d rho. So let's see that. So now if I have a sphere of radius rho and another one that's slightly bigger of radius rho plus delta rho, and then I have a little box in here, then I know that the volume of this thing will be essentially, well, its thickness. The thickness is going to be delta rho times the area of its base, or top, doesn't really matter, which is what we've called delta S. Okay, so we'll get A becomes rho now, square sine phi delta rho delta phi delta theta. And so out of that we get the volume element in spherical coordinates, which is rho squared sine phi d rho d phi d theta. And that's a formula that you should remember. Okay, so whenever we integrate a function and we decide to switch to spherical coordinates, then dx dy dz or r dr d theta dz will become rho squared sine phi d rho d phi d theta. Okay, any questions on that? No. Okay, so let's see how that works. So as an example, remember at the end of the last lecture, I tried to set up an example where we were looking at a sphere sliced by a slanted plane. And now we're going to try to find the volume of that spherical cap again, but using spherical coordinates instead. So I'm going to just be smarter than last time. So last time we had set up these things with a slanted plane that was cutting things diagonally. And if I just want to find the volume of this cap, then maybe it makes more sense to rotate things so that my plane is actually horizontal and things are going to be centered on the z-axis. So in case you see that it's the same, then that's great. If not, then it doesn't really matter. You can just think of this as a new example. So I'm going to try to find the volume of a portion of the unit sphere that lies above the horizontal plane z equals 1 over root 2. Okay, 1 over root 2 was the distance from the origin to our slanted plane. So after you rotate, that's how you get this value. Anyway, it's not very important. You can just treat that as a new example if you want. Okay, so we can compute this in actually pretty much any coordinate system. And also, of course, we can set up not only the volume, but we can try to find the moment of inertia about the central axis or all sorts of things. But I'm just doing volume for simplicity. So actually, this would go pretty well in cylindrical coordinates, but let's do it in spherical coordinates because that's the topic of today. A good exercise, do it in cylindrical and see if you get the same thing. So how do we do that? Well, we have to figure out how to set up our triple integral in spherical coordinates. So remember, we'll be integrating 1 dv. So dv will become rho squared sine phi d rho d phi d theta. And now, as we start, we're already facing some serious problem. We want to set up the bounds for rho for a given phi and theta. So that means we choose latitude, longitude. We choose which direction we want to aim for, which point of the sphere we want to aim at. And we're going to shoot a ray from the origin towards this point, and we want to know what portion of the ray is in our solid. So we are going to choose a value of phi and theta, and we're going to try to figure out what part of our ray is inside this solid. So what should be clear is at which point we leave the solid, right? What's the value of rho here? It's just 1. The sphere is rho equals 1. That's pretty good. The question is, where do we enter the region? So we enter the region when we go through this plane, and the plane is z equals 1 over root 2. So what does that tell us about rho? Well, it tells us, so remember, z is rho cosine phi. So the plane is z equals 1 over root 2. That means rho cosine phi is 1 over root 2. That means rho equals 1 over root 2 cosine phi, or as some of you know it, 1 over root 2 times secant phi. Okay, so if we want to set up a bounds, they will start with 1 over root 2 secant phi all the way to 1. Okay. Now, what's next? Well, so we've done, I think that's basically the hardest part of the job. Next, we have to figure out what's the range for phi. So the range for phi, well, we have to figure out, how far to the north and to the south our region goes. Well, the lower bound for phi is pretty easy, right? Because we go all the way to the North Pole direction. So phi starts at 0. The question is, where does it stop? To find out where it stops, we have to figure out what is the value of phi when we hit the edge of the region. Okay, so maybe you see it, maybe you don't. One way to do it geometrically is to just, it's always great to draw a slice of your region. So if you slice these things by a vertical plane, or actually even better, a vertical half plane, so I'm going to delete one half of the picture. So I'm going to draw these R and Z directions as before. So my sphere is here. My plane is here at 1/√2, and my solid is here. So now the question is, what's the value of phi when I'm going to stop hitting the region? And so if you try to figure out first what is this direction here, that's also 1/√2, and so this is actually 45 degrees, also known as pi/4. The other way to think about it is at this point, well, rho is equal to 1 because you're on the sphere, but you're also on the plane, so rho cos phi is 1/√2. So if you plug rho equals 1 into here, you get cos phi equals 1/√2, which gives you phi equals pi/4. That's the other way to do it. You can do it either by calculation or by looking at the picture. Okay? So either way, we've decided that phi goes from 0 to pi/4. So this is pi/4. Finally, what about theta? Well, because we go all around the z-axis, we're going to go just 0 to 2 pi. Okay, any questions about these bounds? Okay, so note how the equation of this horizontal plane in spherical coordinates has become a little bit weird. But if you remember how we do things, say that you have a line in polar coordinates and that line does not pass through the origin, then you also end up with something like that. You get something like r equals a secant theta or a cosecant theta for horizontal or vertical lines. And so, it's not surprising you should get this. That's in line with the idea that we are just doing, again, polar coordinates in the RZ directions. Okay? So, of course, in general, things can be very messy, but generally speaking, the kinds of regions that we'll be setting up things for are no more complicated or no less complicated than what we would do in the plane in polar coordinates. Okay, so there's, a small list of things that you should know how to set up, but you won't have some really, really strange thing. Yes?
Can you explain how we found the rho again, please?
The rho, oh, you mean the bounds for rho? Yes. So in the inner integral, we are going to fix values of phi and theta. So that means we fix in advance a direction in which we're going to shoot a ray from the origin. So now as we shoot this ray, we're going to hit our region somewhere, and we're going to exit again somewhere else. Okay, so first of all, we have to figure out where we enter, where we leave. Well, we enter when the ray hits the flat face, when we hit the plane, and we will leave when we hit the sphere. So the lower bound will be given by the plane, the upper bound will be given by the sphere. Okay? So now you have to get spherical coordinate equations for both the plane and the sphere. For the sphere, that's easy, that's rho equals 1. For the plane, you start with z equals 1/√2, and you switch it into spherical coordinates, and then you solve for rho. And that's how you get these bounds. Is that okay? All right. So that's the setup part. And of course, the evaluation part goes as usual. And since I'm running short of time, I'm not going to actually do the evaluation. I'm going to let you figure out how it goes. Let me just say, in case you want to check your answers, so at the end, you get 2 pi over 3 minus 5 pi over 6 root 2. Yes, it looks quite complicated. That's basically because you get 1 over, well, you get a secant square when you integrate. See, when you integrate rho squared, you will get a rho cubed over 3, but that rho cube will give you a secant cube for the lower bound. And then when you integrate sine phi secant cubed phi, you do a substitution, you see that integrates to 1 over secant square with a factor in front. So, and the secant square, when you plug in, no, that's not quite all of it. Yeah, well, the secant square is one thing, and also the other bound you get sine phi, which integrates to cosine phi, so you get anyway, you get lots of things. Okay, enough about it. So next I have to tell you about applications, and of course, well, there's the same applications that we've seen last time, finding volumes, finding masses, finding average values of functions. In particular now, if it says, find the average distance of a point in this solid to the origin, well, spherical coordinates become appealing because the function you're averaging is just rho, while in other coordinate systems, it's a more complicated function. So, if you're asked to find the average distance from the origin, spherical coordinates can be interesting. Also, well, there's moments of inertia, preferably the one about the z-axis, because, if you have to integrate something that involves x or y, then your integrand will contain that awful rho sine phi sine theta or rho sine phi cosine theta, and then it won't be much fun to evaluate. So, but anyway, there's the usual ones. And then there's a new one. So, in physics, you've probably seen things about gravitational attraction. If not, well, it's what causes apples to fall and other things like that as well. So anyway, physics tells you that if you have two masses, then they attract each other with a force that's directed towards each other, and in intensity is proportional to the two masses and inversely proportional to the square of the distance between them. So if you have, a given solid with a certain mass distribution, and you want to know how it attracts something else that you will put nearby, then you actually have to, the first approximation would be to just say, well, let's just put a point mass at its center of mass. But if your solid is actually not homogeneous or has a weird shape, then that's not actually the exact answer. So in general, you would have to just take every single piece of your object and figure out how it attracts you, and then, compute the sum of these. So for example, if you want to understand, why anything that you drop in this room will fall down, you have to understand that, Boston is actually attracting it towards Boston, and Somerville is attracting it towards Somerville, and lots of things like that. And China, which is much further on the other side, is going to attract it towards China. But there's lots of stuff on the other side of the Earth, and so overall, it's supposed to end up just going down. Okay, so now how to find this out? Well, you have to just integrate over the entire Earth. Okay, so let's try to see how that goes. So the setup that's going to be easiest for us to do computations is going to be that, we are going to be the test mass that's going to be falling, and we're going to put ourselves at the origin. And the solid that's going to attract us is going to be, wherever we want in space. You'll see, putting yourself at the origin is going to be better. Well, you have to put something at the origin, and the one that will stay a point mass. In my case, I'm not really a point, but anyway, let's say that I'm a point, and then I have a solid attracting me. Well, so then if I take a small piece of it with a mass delta m, then that portion of the solid exerts a force on me, which is going to be directed towards it, and will have intensity. So let's see. So the gravitational force exerted by a mass delta m at a point of xyz in space on a mass m at the origin, well, we know how to express that. Physics tells us that the magnitude of this force is going to be, well, g is just a constant, okay? It's the gravitational constant, and its value depends on which unit system you use. Usually it's pretty small, times the mass delta m times the test mass little m divided by the square of the distance. And the distance from you to that thing is conveniently called rho, since we've been introducing spherical coordinates. So that's the size, that's the magnitude of the force. We also need to know the direction of the force, and the direction is going to be towards that point. So the direction of the force is going to be that of xyz, but if I want a unit vector, then I should scale this down to length 1. So let me divide this by rho to get a unit vector. So that means that the force I'm getting from this guy is actually going to be g delta m over rho cubed times xyz. I'm just multiplying the magnitude by the unit vector in the correct direction. Okay, so now if I have not just that little piece delta m, but an entire solid, then I have to sum all these guys together, and I will get a vector that gives me the total force exerted. Okay? So of course, there's actually 3 different calculations in one, because you have to sum the x components to get the x component of the total force, same with the y and same with the z. So if you look just, say, at the, well, let me first write down the actual formula. So if you integrate over the entire solid, oh, and I have to remind you, well, what's the mass delta m of a small piece of volume delta v? Well, it's the density times the volume. So the mass is going to be, sorry, density is delta, it's a lot of Greek letters there, times the volume element. So you will get that the force is the triple integral over your solid of g m xyz over rho cubed delta dv. Now, 2 observations about that. So the first one, well, of course, these are just constants, so they can go out. The second observation, so here we are integrating a vector quantity. So what does that mean? I just mean the x component of the force is given by integrating gmx over rho cubed delta dv. The y component, same thing with y. The z component, same thing with z. Okay, there's no like, just integrate component by component to get each component of the force. So now we could very well do this in rectangular coordinates if we want, but the annoying thing is this rho cubed. See, rho cubed is going to be x squared plus y squared plus z squared to the 3 halves. That's not going to be a very pleasant thing to integrate. So it's much better to set up these integrals in spherical coordinates. And if we are going to do it in spherical coordinates, then probably we don't want to bother too much with x and y components, because those would be unpleasant. They would give us rho sine phi cos theta or sine theta. So the actual way we'll set things up is to place the solid so that the z-axis is an axis of symmetry. I mean, of course, that only works if the solid has some excess of symmetry. You know, like if you're trying to find the gravitational attraction of, I don't know, the pyramid of Gizeh, then you won't be able to set it up so that it has a rotation symmetry. Well, that's a tough fact of life, then you have to actually do it in XYZ coordinates. But if at all possible, then you're going to place things, well, I guess even then you could center it on the z-axis. But anyways, you're going to mostly place things so that your solid is actually centered on the z-axis. And what you gain by that? Well, what you gain by that is that by symmetry, the gravitational force will be directed towards, you know, along the z-axis. So you'll just have to figure out the z component. So then the force will be actually, you know in advance, that it will be given by 0, 0, and some z component. And then you just need to compute that component. And that component will be just g times m times triple integral of z over rho cubed delta dv. Okay, so that's the first simplification we can try to do. The second thing is, well, we have to choose our favorite coordinate system to do this. But I claim that actually spherical coordinates are the best. Because let's see what happens. So g times mass times triple integral. Z, well, z in spherical coordinates becomes rho cosine phi over rho cubed. Density, well, we can't do anything about density. And then dv becomes rho squared sine phi d rho d phi d theta. Well, so what happens with that? Well, you see that you have a rho squared, and a rho cube that cancel each other. So in fact, it simplifies quite a bit if you do it in spherical coordinates. So the z component of the force, sorry, I'm putting a z here to remind you it's the z component. That is not a partial derivative, okay? Don't get things mixed up. Just the z component of the force becomes gm triple integral of delta cos phi sine phi d rho d phi d theta. And so this thing is not dv, of course. dv is much bigger, but we've somehow canceled out most of dv with stuff that was in the integrand. And see, that's actually suddenly much less scary. Okay, so just to give you an example of what you can prove in this way, you can prove Newton's theorem, which says the following thing. It says the gravitational attraction of a spherical planet, I would say with uniform density. Or actually, it's enough for the density to depend just on distance to the center, but let me just simplify the statement. Is equal to that of a point mass with the same total mass at its center. Okay, so what that means is that, so the way we would set it up is you would be sitting here, and your planet would be over here, or if you're at the surface of it, then of course you would just put it, tangent to the xy plane here, and you would compute that quantity. Computation is a little bit annoying if the sphere is sitting up there, because of course you have to find bounds, and that's not going to be very pleasant. The case that we actually know how to do fairly well is if you're just at the surface of the planet. But then what the theorem says is that the force that you're going to feel is exactly the same as if you removed all of the planet and you just put an equivalent point mass here. So if the Earth collapsed to a black hole at the center of the Earth with the same mass, well, you wouldn't notice the difference immediately, or rather you would, but at least not in terms of your weight. Okay, that's the end for today.